for me to have the opportunity to speak. And thanks everybody who came to the talk. I don't know if this is acceptable to how you organize things usually, but if people want to ask questions during the talk, that's great. And maybe it's better so that there's no misunderstandings. And if someone has a question that should be asked immediately, please do so. And so I will talk about some applications of Groebner basis to multivariate cryptography. But before I got to that, I wasn't sure. So I thought that this talk was for an audience that was quite mixed and with different backgrounds. So I tried to get there slowly and to also explain how do we get to this kind of questions, what are then the tools that go into it, etc. So there are many applications in which we solve polynomial systems. And this is just because many models in the sciences and in the engineering can be described with polynomial equations. And of course, if these equations are linear, we know very well how to solve linear systems. But when they start being polynomial, the problem becomes a lot more complicated. And this is where commutative algebra, or sometimes people nowadays say nonlinear algebra, comes into play. And I've made here a non-exhaustive list of applications which are really more, the tool is always the same, and then the goal, what we do with it is different. So these tools apply in statistics, where there are some models that are described by polynomial equations. In biology, to describe the dynamics, to describe and study the dynamics of chemical reaction networks. I will talk in this talk a little bit about coding theory and cryptography. But as I said, they appear also in more applications, including, for example, computer vision, where you try to reconstruct, for example, 3D images from a bunch of 2D pictures, etc. Okay, so as I said, so the type of applications that I study are in communication, and specifically to coding theory and cryptography. So what's the model here? So we want to communicate over a channel, and so I call source the one that emits the message. Okay, so when you have a message, maybe you want it to stay private, so you don't want that other people except for the intended recipient can read your message. And in that case, you use cryptography to do that. And that means you encrypt the message. So you can think of that. We will come back to this later, but this is just kind of like scrambling the message in order to make it unintelligible. And once you have done that, your message cannot be read by third parties. And then you encode it. And by encoding, I mean you use coding theory. And the goal of coding theory is to add a redundancy to your message that you're going to send, in order to be able to then correct errors that may occur during transmission. So then the message is encrypted, encoded, then it gets sent over the channel, and maybe there will be some noise. Obvious examples of situations where you coding theories, for example, is in space transmission, where there's a lot of phenomena that make some of your message be lost or corrupted. And then once the message reaches the destination, you undo all you had done before. So you decode. Yes? Okay. So you decode, and by decoding, I mean you correct errors if there were any, and then you undo this encoding procedure, and then you decrypt, and then the sync, so the receiver receives the message. Okay, so I will say a few words about these two steps of encryption and encoding. I start from encoding. So encoding, as I said, is you want to correct errors. And if you do this over a network, the right algebraic models to do this, the right way to do this algebraically is to encode your messages into matrices. So unfortunately, I don't have time to explain in detail how it all works. So I guess you'll have to take some things for granted. And then if you have questions, I'm happy to say more later. So there you encode your message. So you associate to your message, you represent your message in the form of a matrix. And then the matrix is sent over the network. So each row is sent. And so a code here is a subspace of matrices, a linear subspace of matrices over a finite field. Usually in this setting, everything is finite because it just works better with the architecture of the computer. And then you have a notion of distance. And here, the distance of two matrices is the rank of their difference. Okay, and so now, one very important, or probably the most important parameter of a code in this setting is the minimum distance. And the minimum distance is the minimum of all the distances of pairs of distinct elements of your code. So it's the minimum, if you are in a linear space, it's the minimum rank of a non-zero matrix in your linear space. And for example, just to make it concrete and so that it's clear for everybody. So here we have our code, which consists of the vector space generated by these two matrices. And of course, then you also have the zero matrix and you have their sum, which is the matrix that has 0, 1, 0 on the diagonal. And so all the non-zero matrices have rank 2, and so the minimum distance here is 2. And the minimum distance is important because the larger the minimum distance, the more errors you can correct. And now let me say a word about this. So assume you have your code. So the code can be thought again as the set of your messages. And then an element of the code is sent and something else is received. So there is some error, and what you receive is not what was originally sent. And it's not even something inside the code. It's just some matrix where some entries have been changed. And now the decoding problem is you want to recover the M that was sent from the N which is received. So the information you have is the code and the N which you received. And the way you do this is you solve this problem. So you find the element in the code, so the linear combination of the generators MI of the code, which is closest in distance to N. And now, in practice, what you do is you minimize the rank of a matrix where the entries are linear forms in the Xi's. Okay. Yeah, and this minimizing the rank somehow, again, I don't want to get too much into detail, but this minimizing the rank intuitively means that you assume that the least number of error possible has occurred. So you assume that what was sent is the closest thing to what you have received. So you correct the least possible and you get something that makes sense. You assume that's your message that was sent to you. Okay, so this is the decoding problem. And this is the most important problem in coding theory, in the sense that that's what you have to solve all the time in order to make your transmission robust, working. And it can be shown, this is easy to show actually, that the decoding problem has a unique solution if and only if the number of errors that occurred is not too much. So if and only if, and you can write it, you can formulate it in this way, the distance between what is received and what was sent is at most this number, which depends on the minimum distance. And this is why the minimum distance is important. And also the other reason why I mentioned this is that this allows us to transform the problem of decoding in a problem that has a polynomial system that we solve. So now, once we have this information, we could say we have N, we have the generators of the code, and we want to find the matrix here, sum of Xi Mi, which minimizes this rank of this difference. And so now we know that this is unique if the rank is at most this much. So in practice, we want to solve this rank of N minus this combination of the MIs, at most a number that we know. And this allows us to write a polynomial system, which is the system that comes from taking minors of appropriate size of this matrix whose entries are linear forms. So this shows how we model this problem in a way that leads us to writing a system of multivariate polynomial equations. And if we knew how to solve this problem, when we know how to solve this problem, we know how to decode our code. Okay, so that's one example of how we want to solve a practical problem in error correction, and this leads us to the solution of a system of polynomial equations. And this problem I call the min-rank problem. And I call it like this because this is a problem which exists independently of coding theory, and it also comes up in cryptography, and I will come back to this problem later in the talk. Okay, so another problem that I want to mention this problem because it's connected to coding theory, but also just because it's a nice algebraic problem. So this problem is matrix completion. Yes, is there a question?
Yeah. In fact, what ensures the existence of xi's in the previous slide?
So let me, go back.
Yeah.
So
find xi's.
How do I find the xi's?
About the existence of xi's. What ensures that?
How about the existence? Yes.
Yeah.
So the thing is this: in coding theory, you assume that they exist because you know that something has been sent to you. So mathematically, existence is not clear. But in this setting, you assume that they exist because you know that someone sent you something. So this M exists. And the fact that the distance is bounded by this number, in fact, is not something that you can always assume, but it's very likely. And so you assume that it's true and you try to solve the problem, and then you see if there is a solution. So this is what one does in practice.
Thank you. There is another question.
Yeah. Yes, please.
Yes. Hello, good afternoon.
Hello.
Good evening. Please, I want to ask if there is any condition for choosing the matrix. Is there any properties that one will consider in choosing the matrix?
These matrices, you mean?
Yes.
The generator of the code, yes. So obviously there is a whole theory to this, right? Which unfortunately I did not explain so much in these 2 slides, but yes. So how you choose the matrices is very important, and this is what gives you a good code. And you also want, in fact, to solve this problem, if you really want to be honest, you would rather not solve a polynomial system. You would rather have a more efficient method. And so you try to make a good choice of the MIs that allow you to solve this problem here efficiently. So when you construct a code, you want to choose matrices that give you a large minimum distance, because that gives you good error correction, and that gives you an efficient way to solve this problem. And so this is all connected to code construction, and this is a very active field where, whenever you can make a good choice for the matrices, you have a code essentially. So there's many techniques that people use, and this is an active area of research. I don't know if I answered your question.
You have answered. Thank you. You have answered. Thank you.
Okay, great. Excellent. So I was saying about matrix completion. So matrix completion is the problem of you have a matrix where some entries are known and some entries are not known, and you want to fill the missing entries so that the matrix has least rank. So you see, this is very close to the problem from before, right? It's a rank minimization problem. And sometimes you are happy enough to have small enough rank. So not necessarily in applications, often you don't necessarily need to have the minimum, but it's enough to have something which is small enough. And so, as I said, this is a special case of matrix completion, because you could put different variables in each entry that you don't know, and that would give you a matrix whose entries are linear forms. Okay, and this problem arises, these 2 problems, matrix completion and min rank, arise in many areas. As I said, I mentioned in coding theory, we will see that it comes also in cryptography. And I will make now another example of a problem which has to do with matrix completion, and this is the Netflix problem. So In the Netflix problem, you're given a rating matrix, which is a matrix where there is a customer, and there is there is a customer that watches several movies, and the customer gives certain ratings to the movies. And then there will be movies that the customer has not yet watched, and these are the entries that we don't know yet in the matrix. And what you do is you minimize the rank of this matrix, and this gives you a way to predict whether a user would like or maybe not like a certain movie. And the low rank assumption corresponds to assuming that preferences depend on few factors, or that usually people will prefer the same things if you have a large group of people. So, okay, so so this is another example of how this low rank completion comes into the applications. And there is also a situation in which it arises in coding theory. So in coding theory, there's a problem which is called index coding. And there, index coding asks you to find an optimal coding scheme for broadcasting multiple messages to receivers which has different side information. So what does this mean? It means you have an antenna, and then you have many users, and these users want to receive certain information, which I call by variables. So this first user wants to receive information 1, the second user 2, etc. And they also have some cache, so they have something that they know already because maybe there was a previous transmission and they already have some informations. And the tower can only broadcast. So the tower does not send punctual messages to each one separately, but the tower makes a transmission and everybody will be able to listen to it. And so the problem is the tower wants to make everybody happy, but also wants to send the least number of transmission. So if the tower can only send either X1 or X2 or X3 or X4, it will have to do 4 transmissions. But the trick here, you can also send linear combinations of the informations of the messages. And so the tower wants to minimize the number of things that it sends. And in this case, you can verify that if the tower sends X1 plus X4 and X1 plus X2 plus X3, everybody is happy. For example, we look at the third receiver. The third receiver wants to have X3. And so if he receives X1 plus X2 plus X3, and then he has X2, then he will have X1 plus X3. And he will also have X1 plus X4, so X1, and so he can recover X3, X4, X3, etc., etc. So you can go ahead and verify that each user will be happy with this. And how do we find this solution, right? So the tower wants to be able to find what are the things that they should transmit. And this is again a matrix completion problem. So you can form a matrix where you put, so the rows are the people that want to, so the receivers, and the columns are the 4 messages. And now, for example, receiver 3 here, they request X3, so I will put a 1 in the X3. So they have 2 and 4. So I put an unknown in 2 and 4 because essentially they may or may not use this information. And this is the thing that I want to be able to compute. And a 0 and X1 because they do not have X1. And they are not interested in receiving X1 either. So they don't need any X1. I put a 0. And I do that for everyone. And now if we find a completion of least rank, this will have rank 2, I think. So the rank of the completion is the number of messages that has to be broadcasted. And, oh, sorry, I thought I had the completion, but I don't. So, and in this case, you can compute that the rank of the completion is 2, and the row space is generated by these 2 rows. And this is why I find how I can find these 2 rows. Okay. So this is another example of application of matrix completion. Okay. In coding theory. And now I come to cryptography. So this is my last application of polynomial system solving, and then I come to polynomial system solving. So in cryptography, one of the big the big deal lately in cryptography is post-quantum cryptography. The idea in post-quantum cryptography being that if a quantum computer were to be built, the public key crypto systems that we use nowadays and which are based on the discrete logarithm problem and factoring will become useless because these problems will become easy to solve. And so multivariate cryptography and other proposals in post-quantum cryptography become relevant because these systems are based on problems which are supposed to stay hard on a quantum computer. So the reason why this is relevant is that, once again, the reason why this is relevant is that we believe that even with a quantum computer, this encryption system will stay secure. Okay, and how do we build this system? So we work over a finite field, and we select m equations in n variables with coefficients in that finite field. These are usually quadratic, but they don't need to be. And they are usually quadratic for simplicity, because linear is easy, quadratic is the first one, which is not easy to solve, okay? And then now you define a map by evaluation. And this map, you want to disguise it. So you want to hide it from the others. And so what you do is you multiply it left and right by random affine linear maps, which means you make a random linear change of variables inside. And instead of writing down Q1, Qm, you write random linear combinations of them, okay, M, okay? So this is the private information, is the Q, and the two transformation T and S that you use to disguise it. And the public information, now I will say what this means in a second, is the result of the composition. So the polynomials that you got after you disguise this Q1, Q1, okay? And now there is this allows you to set up a public key crypto system in the following way. So the goal of a public key crypto system is that once you have constructed it, you publish it, and then everyone can use it to send you messages which are confidential, in the sense that you are the only one who can decrypt and read them. So with this setup, okay, the public information will be this F1, Fm. And now to encrypt a message, so usually in cryptography, the two parties are always called Alice and Bob. So if Bob is the creator of the system and Alice wants to send a message to Bob, and so in order to encrypt the message, Alice takes the message alpha and computes P of alpha and obtains beta. So alpha is the secret message, beta it's the encryption, and it's computed using this public information. And now Bob, who constructed the system and is the intended receiver of the message, he knows not only P, but he knows all the ingredients that he used to construct P. So he knows P, Q, S, and T. And so he can invert each one of them individually. So he can compute T inverse, Q inverse, S inverse. And the trick here is that Bob will have to construct a Q so that the inverse can be computed efficiently. Okay, and maybe just one more word about this. So this is not at all obvious how to do this. And in fact, each time you can come up with such a Q, you have a crypto system. Okay, so there are some ideas floating around on how people will construct this Q. Each idea will lead to a different crypto system, but this is just kind of the basic setup. So whenever you can come up with such a Q, you have a crypto system following these steps, okay? And now the point is that, and in this way, you can also produce a signature. Maybe I don't want to insist too much on this. I'll just talk about the security. So what's the security? The security is how hard is the task of an adversary who wants to read your message without being the intended receiver. So this is usually called Eve, from eavesdropper. So the task that Eve has to solve in order to decrypt is she knows P because P's public is known to everybody. She knows beta because beta was sent over the channel and she was maybe able to read it from the channel. And so she wants to find the alpha such that P of alpha is equal to beta. And so in order to do that, she has to solve a system of polynomial equations. Or maybe she doesn't have to. It's not really precise to say she has to. She doesn't have to, but that's a way she could solve the problem. She could solve this system of polynomial equations. And so notice that Eve only knows the P. She doesn't know the Q, S, and T. Yes.
What about the existence of the inverse?
Yeah, you assume that the inverse exists. So when you construct Q, in this case, I'm assuming that it exists, but when you construct Q, you want it to be injective. And then it will be invertible on the image. So that's, yeah, part of the requirements to have something that works.
Thank you.
Yes? Another question?
Sorry, please. In constructing the private key, can the private key and the public key be identical?
I'm sorry. I
said, can
I
the
do not
private,
hear you very well.
I said, can the private key and the public key be identical?
The identity?
Identical. He said
Identical.
that public key and
identical.
private.
Oh, you don't want them to be identical because, I mean, from the setup that I give, I guess they could be, but you don't want them to be, right? Because if you were to reveal the Q, remember that the Q has to be easy to invert. And then if you were to reveal the Q to everybody, then everybody could invert simply, and then they could read your messages. So here, the point is you have a trick, which is the fact that the Q can be inverted easily. You hide it so nobody else sees it. So of course, the S and the T could be the identity, but you don't want them to be because you use them to hide the Q, right? So you pick them at random. This is usually how it's done, okay? So that they move things around as much as possible. And now you have P from, and the assumption here is also that from P you cannot recover Q.
Thank you.
You're welcome. Are there any other questions about this? Okay, so anyway, you know, I know it's a lot of information, maybe, you know, I just wanted to give the flavor of how the polynomial systems come about, right? But maybe the important information here is there is a polynomial system, and usually polynomial systems are hard to solve. And now, in this case, there is also a trick that allows Bob, the intended receiver, to easily solve the system. And everybody else will just have to go ahead and solve a system which does not look like it has any specific properties or anything that we can use to solve it easily. And so that will be a hard problem for everyone else, except for Bob, who can then be the only one who can decrypt. Okay, so then here, the security relies on the fact that the adversary, so Eve, cannot solve the system. Okay, and so it relies on a problem which is usually called a multivariate quadratic problem. And this problem is the problem of computing the solution of a system of equations, maybe quadratic if you speak about multivariate quadratic, over a finite field, over a field in general, but in our case, it will be a finite field. And, oh, sorry, this is cut. So we assume throughout that the system has a finite number of solutions, not only over the finite field, obviously, because that's obvious, but that's trivial, right? But over the algebraic closure. And then in this situation, you could find the solutions by computing a Groebner basis. And so the complexity of computing a Groebner basis gives you an upper bound on the security of the system. And this is why it is very important in this context to be able to find upper bounds on the complexity of computing Groebner basis. Okay, so now I will say a few words. So I don't assume that everybody knows about Groebner basis. So maybe if you do, maybe you can tell me. So I assume that people, maybe not everybody remembered or Groebner basis. So I made a quick summary of what Groebner bases are. Okay, so whenever possible, I speak just over a field and not just over a finite field, because many of these things do not depend on the field. So we are in a polynomial ring over some field with coefficients in some field. And there, a monomial is a product of powers of variables. For example, x1 cubed, x3, x4 squared is a monomial. Okay. And now on the monomials, you put an order. And this order is called the term order. And we ask that this order is total. So every pair of monomials is comparable. You know which one is the biggest and which one is the smallest. We ask that it's multiplicative. That means if you have an inequality between two monomials and you multiply both sides by the same monomial, the inequality stays, satisfied, stays. And you ask that one is the smallest monomial. And this is called being a well ordering and ensures termination of the algorithms. So once you have this set up, okay, and I have some examples of term orders now. So if you have only one variable, there is no choice of order, because this rule tells you that 1 is less than x, and now you multiply both sides by x, you get that x is less than x squared, and then you keep going like this, and you see that the powers are ordered in increasing degree, the powers of x. So if you have one variable, there's no choice, there's only one order. But if you have more variables, there will be more orders, and I have two examples here. So the first one is the lexicographic order. The lexicographic order is the order of the dictionary. So it's the order in which you put the words in the dictionary. So you order the variables. For me, I always think x1 is the biggest, then x2, then x3. So now I go look at the things I want to compare, and I see this one has x1, this one does not, so this one is bigger. And now I compare these two. They both contain x1, but this one contains more copies, so this will be bigger. Or for example, if I want to compare these two, I look at x1, and they are both multiplied by x1, so they tie in a sense, right? And now I go look at x2, this has a bigger power of x2, and so this one, it will be the biggest. So this is one order, which is called lexicographic. And then there is another order, and these are the two that will interest me for this talk, which is called degree reverse lexicographic. And in this order, to compare two monomials, first you look at the degree, and you see which degree is bigger. If one of them is bigger, that will be the bigger monomial. If they are the same, then you do something similar to before, but you start from the smallest variable, and you say things that contain the smallest variable are smaller. Before you said things that contain the biggest variable are bigger. Now you say things that contain the smallest variable are smaller. And this actually is not the same as before. It could seem, if you don't, at a first approximation, it could seem, but it's not the same. And for example, here, I look at x1, x3, and x2. This one is bigger because it has larger degree. Then I look at these two. They both have degree 3. And now I look, this one is divisible by x3, and this one is not. So this one is smaller, etc. And again, I can look here. They both have degree 5. They are both divisible by the same power of x3. And then I go look at the next variable. I look at x2. This one is divisible by x2 squared, this one by x2. And now this is the smallest because it has the largest power of the smaller variable. Okay. So these are the orders. And now I take my equations, and I look at the ideal that they generate. So the ideal is the set of combinations of my equations with coefficients in the ring. So coefficients are again polynomials. So this is the ideal generated by my polynomials. And for each polynomial, I can take the leading term, which means when I write my polynomial as sum of monomials, I will take the bigger one in the order that I have chosen. Okay. And I could do that for all the polynomials in my ideal. Okay. And so I could take all those monomials. Maybe they will be infinite many if the field is infinite. Okay. I take them all and I take the ideal generated. And this ideal is called the initial ideal of I. But this ideal is finally generated. And so there will be S polynomials, a certain number of polynomials that whose leading term generate this ideal. And this I call a Groebner basis, okay, of the ideal. So I have an example just to give a flavor of how this works. So I take two variables, x1, x2, and I take lexicographic. So if I take this polynomial here, the leading term is this one because it contains the x1 and the other one doesn't, okay? And now I take two generators for my ideal. One is this one, the other one is x1 squared plus x2 squared. So this one will be bigger. So in my initial ideal, I will have the leading term of this, x1 squared, the leading term of this, x1, x2 squared. And then what turns out is that I can produce another polynomial here in the ideal, I wrote it here, which is x2 to the fourth. So x2 to the fourth, if I look at the generators, it's not obvious, but in fact, it is also in my ideal. And so now it means that x2 to the fourth has to be also in the initial ideal because it's the leading term is obviously itself. And in fact, it turns out that this is all. And so I have a Groebner basis now. I have to take all the polynomials that give me, I have to take for each monomial generator, I have to take a polynomial that has that leading term in my ideal. So I take the two that I had before and x2 to the fourth, the ones that I had already computed. And so this is a Groebner basis. Okay. So I guess what's important for the purpose of this talk is that Groebner bases exist, they are finite, and they are not necessarily the generators that you started from. So the problem here will be how can we compute them? Okay. Whoop. Sorry about that. I don't know what I did. Okay. 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 So and this is why Groebner bases are useful. So forget about the hypothesis. I like to write things correctly, but the point of this lemma is this, that when you compute a lexicographic Groebner basis under some reasonable assumptions, it has this form here. And in particular, you see here, there is one polynomial which is only in the variable xn. And then there are some other polynomials that are xi minus a polynomial in xn only. So this Groebner basis tells us exactly what are the solutions of the system. Okay, and why is that? Because what I can do now is, if I want to solve a system, I can compute a Groebner basis of the ideal that the system generates. Then I look at this univariate polynomial, I find its solutions, and then for each solution, I plug it in all these polynomials to find the value of the other variables. So once you have the Groebner basis, this shape lemma tells you that you have the solutions of the system. Okay, so this is why this theorem is why Groebner basis allow you to compute solutions. Okay. Oh, I'm sorry, I don't know what I'm doing. Okay, here I have some hypotheses, but I guess it's not really necessary to get into all the hypotheses. All I'm trying to say here is that these hypotheses are often true, and if they're not true, you can make them be true after doing some modification to the system. Okay. Now, how do we compute a Groebner basis then? Okay, so the attacker, if we imagine to be the attacker wants to compute the solutions of a system. In order to have the solutions of the system, they could compute a Groebner basis. So how do we compute a Groebner basis? So that's the problem at the core of the security. And this seems to be nowadays the most efficient are linear algebra-based algorithms, and these are based on an idea of Lazare from the 80s, and they are now implemented in many ways with also improvements and some additions to them. And the most popular implementations are F4, F5, and Excel and its variants, which Excel stands for extended linearization. It's presented in a way which is a little bit different from Groebner. It doesn't say, like, they never say Groebner basis, but it's the same. It's essentially the same. Okay, and how do we compute the Groebner basis? So I have a system with certain equations, and now I pick a degree. I pick a degree D, and I go and write a matrix for that degree. So the rows of my matrix will correspond to the polynomials in my system of degree up to D. And I can also put my polynomial multiplied by monomials as rows, okay? So up to degree D always. And the columns will correspond to the monomials of degree up to D, and I order them in the order that I have chosen. For example, lexicographic, okay? And now how does the algorithm work? I write down this matrix where in each row corresponds to a polynomial, and I write it in the basis of the monomial. So I write the coefficients. Then I compute a reduced echelon form, and this spits out a Groebner basis maybe, or maybe not. And if it doesn't, I go to the next degree. And either I have the Groebner basis or I keep going. And the point is that it can be proved that this process will stop and give a Groebner basis. Okay, so this is the basic version of a linear algebra-based algorithm. And in the next slide, I will make an example of this. Okay, so let's say that these are my polynomials. I want to solve, I mean, the example is very small and it's very easy to solve, but it's just to give an idea. Okay, so I want to solve these two polynomials and the order is lex. So in degree 2, I start in degree 2 because the equations are in degree 2. So that's the reasonable place to start. So now I put my monomials, all the monomials of degree up to 2 in the columns, and in the rows will be my polynomials. And there are only these two, so I just put these two. And you see, for example, F2 is x2 squared minus 1. So I put here the coefficients, right? This is how I write things in the rows. X1 squared as coefficient 0, x1, x2 as coefficient 0, x2 as coefficient 1, and 1 as coefficient minus 1. Okay, so now I compute the reduced echelon form, which actually is already, and I have not found anything new, and so I haven't gotten anything yet. Okay, so this is the matrix in degree 2. It doesn't do anything for me. Now I go to degree 3. In degree 3, I have many more monomials and many more polynomials because I can put the one from before, but I can also multiply them by variables up to go to degree up to 3. Okay, so I write all these polynomials in my matrix, and now I compute the reduced echelon form. Okay, which I have done before, obviously. And in the rows, you see in red, I have a Groebner basis. So I found my Groebner basis, and we can read it here. It's x1 plus 1, and the other one is x2 squared minus 1. And yes, is there a question?
How would I know that I have to stop here? So I got the Groebner basis. So
oh yeah, that's an excellent question. So yeah, so this is a part of the tricky. This is part of the algorithm, right? I mean, what we want to do here is to bound the degree in which a Groebner basis will pop up. So if I were to do lex, I probably would want to proceed until I get something of the form that was required from before. So for example, here I have a polynomial in x2 only, and then one in x1 and x2. But in general, in practice, what we do is well, I don't know if it's in practice what we do, but what works for the complexity is to say, and now I will give an estimate of what is an upper bound on the degree that I have to compute, and I compute until that degree, and then I know that I have a Groebner basis. Another thing that you could do is you could check as polynomials. I imagine maybe you are familiar with as polynomials. So you could do you could do a termination criterion. So a check that you do at each degree, and it tells you are done or you are not done. Okay.
Okay.
Yeah. Okay. So, and now we have the Groebner basis, and the point here is up to which degree do I have to compute? Okay. This is the thing we want to know. Okay, and so this is how we solve a system in practice. We compute a degree reflex Groebner basis. And the reason why we choose this order is because typically with this order, the computation is the fastest. So here we don't only want to solve the system, but we want to do it as fast as possible, as efficiently as possible. So we compute degree reflex, and then we convert the degree reflex basis in a Lex1. And this can be done using an algorithm by Fougère, Gianni, Lazare, and Mora. And for systems that interest us, the complexity is dominated by the first step because, I don't have it here, sorry. So for our systems, the complexity is dominated by the first step because you can go and estimate the complexity of this algorithm and see that if you have few solutions, then this step will be the one that is most expensive. And remember that for cryptographic system, you expect to have only one solution. Okay. So the complexity is dominated by the first step. So that's the part that we have to, if we want to know the security of the system, we want to estimate the complexity of this first step. And that complexity is essentially complexity of Gaussian elimination in a matrix where the rows are the polynomials of degree up to a certain degree, and the columns are the monomials. And you can compute the size of this matrix, and this gives you the complexity. And all this, of course, is controlled by the number, the degree that you have to go up to get the Groebner basis. Like in our previous example, that degree was 3. I started in degree 2, I didn't get anything. When I got to degree 3, I got the Groebner basis, okay? So that's the thing that is important for us. So the invariant that will tell us how, that will control the complexity of this computation, and so that will tell us about the security of the system is this number, this degree, where when you compute that matrix, it gives you the Groebner basis, okay? And that number is called, yeah?
Yeah, what is this M in the summation of A?
Let me go back. So sorry, that's not what I don't know. Let me, I don't know why I was not able to go back into the other slide. Okay, so this M is the number of polynomials in the system. And this is, so for each polynomial M in the system, you will, if you are in degree S, if the polynomial M has degree di, I'm sorry, yeah, I maybe this slide is not very clear. Yeah, no, it says here. So this di is the degree of the ith polynomial. So S minus di is the degree of the monomials that I can multiply by. And so this number is how many monomial multiples of fi do I have in degree up to S. And I sum that overall the polynomials, and this gives you a number of rows of the matrix. And this is the number of monomials of degree up to S in n variables. So this is the number of columns. And so this is the complexity of Gaussian elimination, depends on the number of rows and columns. And really, apart from the exact numbers, the important information here is that everything is controlled by this S, and this S is inside the binomial coefficient. So when I go and compute the number of steps, the actual complexity, the S will go in the exponent, is in the exponent. So the complexity is a function which is exponential in this maximum degree, in this degree where I have to compute, okay?
Okay.
Okay, so, and this number is called the solving degree. Okay, so again, we have fixed degree reverse Lax, and we want to know what is the degree in which Gaussian elimination in this Macaulay matrix will give me the Groebner basis. And this degree, of course, has to be as much, at least, as the degrees of the polynomials that appear in the Groebner basis, right? Because if my Groebner basis has a polynomial of degree 5, I have to at least compute in degree 5 for it to be produced. But it could be bigger, okay? So in general, the solving degree is at least the degrees of the elements of the Groebner basis, and it is equal if the polynomials are homogeneous. But unfortunately, in cryptography, I know only one instance in which the polynomials are homogeneous. So in cryptography, I guess it's fair to say that the polynomials are never homogeneous. And so this is the situation in which you are, that you may have to compute past the degree of the Groebner basis. And if you remember the example that we had before, the one with the Lax, with the two polynomials, in that case, we started from two quadratic polynomials, and we computed the Groebner basis. The Groebner basis had a polynomial in degree 1, a polynomial in degree 2, but in order to obtain it, we had to go to degree 3. In degree 2, you remember, we obtained nothing. So in that case, even though both the input and the output of the computation are in degree at most 2, I have to compute in degree 3. And so this explains, these hints at where is the difficulty here. The difficulty is you want to give a bound on the solving degree, and it could grow bigger. And the question is, how much bigger can it be than the degrees of the polynomials of the system, the degrees of the polynomials in the Groebner base? Okay. Maybe I should wrap up, right? So let me see. Okay, so I had a few more things, but I will just wrap up. Okay, so here I just say what is the homogeneous. So a homogeneous polynomial is a polynomial where all the monomials have the same degree. And if a polynomial is not homogeneous, you can make it homogeneous by taking a new variable and multiplying the monomials of small degree by some powers of that variable. For example, this polynomial has two monomials of degree 3, it's homogeneous. This one has a degree 3 and a degree 1, so it's not homogeneous. And if I want it to be homogeneous, I can make a new variable x0, and I multiply this one by x0 squared, okay? So that's all this slide says, okay? And now how do we bound the solving degree? So there in this work that I said of Lazare, which inspired these algorithms, he proves also, although said in a very different way, that if the system is generic, and then the solving degree is at most the sum of the largest n+1 polynomials in it, the sum of their degrees, minus n. Okay, and in a work with Alessio Caminata, we proved that if the system, you take your system, and your system may be not homogeneous, so you add a new variable, you make all the polynomial homogeneous, then the solving degree, if this is in generic coordinates, which now I say what it means, then the solving degree is upper bounded by an invariant of this, which is called the Castells-Neumann for regularity. And I am not going to define the Castells-Neumann for regularity. I will just say that this is an invariant which is studying commutative algebra, so there is a lot of literature about this invariant. And so sometimes you are able, once you frame the result in this way, like once you frame the problem in this way, now you can use commutative algebra to attack this problem of complexity. And what you have to do is you have to estimate this Castells-Neumann for regularity. And in fact, in a lot of cases, this is even done in many papers. Many people have studied this, so you can just even use sometimes results that were already proved by other people. And it gives you a bound on the solving degree, which is what gives you a bound on the complexity. So on the security of your system. And there is this thing about the generic coordinates, okay? So Being in generic coordinates means that something technical in algebra, but you could think of it like this: that if you look at the solution of the homogeneous systems, these are points in projective space, and none of them is in the hyperplane x0 equal to 0. And so now if you are in this up to a random change of coordinates, this is always true. And now another thing we proved is that if you have the field equations in your system, which you could consider adding if you have a very finite field and the degrees are not too big, then you are in this assumption, and then you always have this bound. And maybe I will just conclude by saying that using this is a starting point. And now using this, we were able to use commutative algebra to produce a lot of estimates of complexity of solving system which appear in cryptography, and therefore as a result we can give estimates on the security of the corresponding systems. Thank you very much.
Thank you, Professor Elisa, for a very nice talk and a very informative one with many practical aspects. So house is open for questions from the participants.
I'm sorry, I really don't know how to raise hand in Zoom,
Yeah.
but I do have a question.
Yes, Imran, go ahead.
Yeah, okay. So these Groebner basis algorithms, that the one you showed, are they implemented in computer algebra softwares?
Yes. So yes, this linear algebra based. Yes. So the usual systems, I don't think they use them. I think they use more like Buchberger's algorithm. So like, for example, Macaulay 2, singular, Cocoa, I think they use all the Macaulay's, Buchberger's algorithm. This F4, F5 is implemented in Magma. It is also implemented by Fougère. He has a distribution that one can get from his webpage, which is called FGB. And it is runs in C. So I personally have a little bit difficulty to use the software because you have to code in C, but to input the polynomials. But this does it also for you. And also there is another system which is called, I think, MSolve by Christian Eder and some other collaborators. And this also computes with this method. So there are some systems, they are just smaller system. And what they do mostly is they solve polynomial system. They don't do all the commutative algebra functionality that we are used to have from Macaulay 2 and the Cocoa and Singular.
So this one is, why do you prefer this one? Because it is suitable for your proofs or computations.
Yeah, so we use this system because if you have to solve, to just compute the Groebner basis, this is much faster. So it's really much faster. So for example, once I could compute something in Cocoa with 1 week, it took 1 week. And then with Magma, it took 1 hour. So it can be, it is not always like this, obviously, but it can be much faster. But it only computes the Groebner basis, so it doesn't do, I don't know, what things interest you to compute. If you want to compute the resolution, for example, it doesn't do it. It just does the Groebner basis. Yeah.
It does the Groebner basis.
Yeah.
Thank you.
Thank you.
Yes, Haruna. Buhari Haruna.
Yes, and thank you. I observed that the algorithm, the encryption algorithm, it is all in numerical form. What if the plain text is given in the alphabetical space? How will someone convert it to the numerical space? I think for someone who is layman would be confusing, as all the algorithms are in numerical form. Then what if it happened that the plain text, it is in the alphabetical form? Thank you.
Yes. So you usually whatever form your message is in, then you will convert it with a bijection into what you call numerical form. So usually you just convert in a string of bits. Bits is like a sequence of symbols over have2. So a sequence of 0 and 1. So usually you do this. For example, ASCII on your machine is just that. There's a correspondence between the symbols that you have in the keyboard and the sequences of 0 and 1s. So there are ways to always convert a text in a sequence of 0s and 1s, and now you have a long vector, and then that's your message.
Thank you.
You're welcome.
Any other question from the audience? Professor Lisa, I have you. Okay, did you try this method with other monomial orders, or because
Yes.
some methods are good with lexicographic, with grade lex, and something grab lex?
So we, for the estimate, we do with degree reverse lex. So this theorem that I said, I mean, I don't know if I was very clear about it, but this theorem that I said of the regularity, this only works for degree reverse lex. And for lex, I think the thing you have to put on the right-hand side is the number of solutions. Because the lex will give you these polynomials that contain the number of solutions, but not only of the system, of the homogenized system. So this could be much bigger, right? Because our system have a few solutions over typically only one solution, but when you homogenize, they will have lots of solutions because they have many equations and higher degrees, sometimes of higher degrees. So that would be a bound for lex, I think, the number of solutions of the homogenization. But the reason, but we don't look at this, and the reason why we don't look at this is because we expect that degree reverse lex will be smaller, and we are interested, and this comes just from the application. We are interested to give the smallest bound possible. Yeah, the smallest upper bound possible.
And secondly, this theorem of Caminata, what you have stated here, so it works only for homogenized F?
Yes.
On the right side.
Yes. So you start from your F, you homogenize each equation, and then the regularity is the regularity of the homogenization. And the thing is, this number, so this F, if it's not homogeneous, I mean, I wouldn't even know. I mean, there's no regularity of F if it's not homogeneous.
This is exactly I was thinking about.
Yeah, I wouldn't know how to define, right? So it's just more somehow. My idea is this, that the homogeneous case is so much easier to treat than the non-homogeneous case. And so what you do is you associate to a non-homogeneous thing a homogeneous one, and then you look at that, and there you can do a lot more, and then you just have to prove that you have an upper bound. But in fact, this is often also an equality. So this upper bound is not a very far upper bound. Yeah.
So did you discuss the case when the equality occurs?
No, we cannot say exactly when the equality occurs. So there are a series of these inequality come from a series of inequalities, in fact, and for some of them we know that generically there will be equality. So over the algebraic closure in a dense open set there will be equality, so almost all the time. But there is one of them where this is not the case, and we are not able to say at this point exactly when this one will be equality.
And what about the ideal with very nice property like ideal with complete intersection property?
Yes, so complete intersection, it will be this case. So if you look on this right-hand side, this is the regularity of a complete intersection of degree d1, dn minus 1. So in this case, you could say it like this. You could say, if I take F homogenize, and now F homogenize is a complete intersection, then the solving degree is the is the regularity of the homogenization. It's less than or equal, but in fact generically equal. Yeah.
Yeah. Thank you.
Yeah.
Thank you very much. Any other question from the audience? I'm done with.
I think there's one more question.
I think the hand raised before. Buhari, do you have any other question?
No, sir. No, sir. Thank you.
No. Okay.
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 So there is a question in the chat,
Let me
which
just
says,
see.
yeah.
Yeah. Can you shed some light on the Groebner basis with respect to resultant method?
Yeah. So that's not, to be honest, I'm not really specialist on resultant, but it is true that resultant method is very close to Groebner basis, and a lot of times you can do the same computation in the two ways. And as far as I understand, especially resultants are very close to the lex. So certainly you can compute also these solutions using the resultants. And I assume because of the closeness with the lex Groebner basis, that maybe this will often not be the most efficient method. But to be honest, I am not sure, because I'm not. So this is what I expect, but I'm not sure, because as I said, yeah, there may be some things about resultants that I don't know. So
yeah. Thank you, Professor Lisa, for a wonderful talk. And let me announce one more thing, that Professor Lisa is going to have a talk in Siam session in upcoming week. Am I right, Professor Lisa?
in no. I actually I stopped now sharing this. So actually I gave a talk already in Siam.
Already.
Yeah,
Okay,
yeah.
in Siam. Okay.
Yes.
And
So yes, I don't have. If people are interested, this talk will be online in the Siam has a website. Sorry, not a website, a YouTube channel. And they put talks in it. And so this talk will be in this YouTube channel.
And also we also have a recording of this talk. Anyone, so all these talks will be uploaded on our website. And please let us join me to thank Professor Lisa once again. And probably she's typing down the website address of Siam. Am I right?
I'm sorry. I was responding. I apologize. I got an email in the chat, and I saw a message in the chat that asked me to send some reference, and I was just replying just.
Okay.
Yes.
So
yeah, the Siam talk you were saying.
no,
Yes. So the Siam.
it is better to share those references with everyone, so that everyone can get the access to those references.
You know what, we can do this. So I had prepared a little more, and at the end maybe I'm always a little optimistic about time, and I didn't get to say everything. So, but I could send the slides to you.
Okay.
And then you could put them online or send them to people as you usually would do. And then at the end of those slides, there is also a reference. So there is also some references of some papers, and there is just a few more things that were not a lot more than what I said, but there is a little bit more than what I said. And there is this paper with Alessio Caminata. There is the paper of Lazar on this way to solve the systems, and people can just email me if they want, and some reference, and I can send.
Thank you once again. Thank you, Professor Lisa, for a wonderful talk. It's we thank you for your time, and thank you all the participants. It's time to advertise our next seminar. So our next seminar is by Gil Kilai. So Elisa knows him, and definitely everyone knows him. That Gil is a special character. So he's very famous for his conjecture, Kalai's conjecture. So now he turned to theoretical computer sciences. So recently he has a paper which states a world without quantum computers. So he will be talking about a world without quantum computer in the next week at the same time. So please do come, do join us for the next seminar. And once again, thank you, Professor Elisa. Thank you, everyone, for your time. Thank you, Elisa, for a wonderful talk.
Thank you so much for inviting me, and thanks everyone for your time and for your interest.
Thank you. Bye-bye. Take care.
Thank you.